Hi, welcome back to my channel. Well, this video is in continuation to the previous video which was made on the same design, that is CRD, completely randomized design, but that was based on equal number of replication. Well, in this video we'll be doing a demo regarding the same design, but the number of replications in this analysis are unequal. For that we have taken an example when an experiment was conducted to study the effect of three drugs, that is A, B, C, where A is replicated 6 times, B 4 times, and C is 5 times, and we have a null hypothesis here, that is A, B, C are same. Now we need to verify whether all these three different drugs or three different treatments are significantly different from each other with respect to the study variable, that is yield. So we have 6 replication for the first treatment, 4 for the second, and 5. So we have a clear case of unequal number of replications. So we will start with getting the totals, which are very important for calculation of sum of squares or the treatment sum of squares. We'll simply click on enter. Then we will simply drag this thing up to the third treatment. Then averages are again important, because we have to do the comparisons. Then we'll click on this enter button, or press rather than on the enter button. Then we have to do one other step, that is to get the squares of these totals, because they are very important as far as these treatment sum of square or drug sum of square is concerned, because in this case the treatments are drugs in this example. So for that we'll use the first total, then square it, raised to power 2, and we'll simply, what we will do, we will drag it up to here. Now the first important step is to get the grand total. Simply we will use this sum function and we will highlight all these. So we have the grand total, and the important step is to get the correction factor. Then correction factor is nothing, it's the square of grand total upon the number of observations. Number of observations here are 15. That is, we will simply get the square of this whole divided by 15. So we have the correction factor, which is very important because this value is to be deducted from each and every sum of squares which will be taken. Now we will start with the first one, that is total sum of square. Total of sum of square is nothing, it's the square of each and every observation. Then what we will do, we'll simply use SUMSQ function. Then we'll highlight all these. Okay, we have sum of squares, but what we have to do, we will deduct this whole value with the correction factor. So we have total sum of square. Now we have the treatment sum of square. In this case we have three different drugs, that is why this is DSS. For that, what we have to do, the normal procedure is to get the square of the totals, which we have done, then divide it with the number of replicates. But each and every treatment is replicated with an unequal number of times. So for that we will simply use this whole divided by 6, because this treatment total of square is replicated 6 times. Then this one is replicated 4 times. Here you can see 4 times. Okay, then this one is replicated 5 times. Okay, then we will get the sum of all these. Then press enter. Now what we will do, we'll simply use this value and deduct this value with the actual correction factor. So we have the treatment sum of square, or we can say the drug sum of square in this example. And error sum of square is very easy to calculate. Simply it is, you have to take the total sum of square minus drug sum of square. So we have error sum of square, we have total sum of square, we have treatment sum of square. So for that we will simply put this value, we'll keep it here. But before that, what we have to do, we'll simply have to adjust what number of degrees of freedom we have. In this case we have 3 drugs, So that is 3 minus 1 is 2, and error is nothing, it is n, the number of observations subtracting the total number of treatments. The number of observations are 15, then 15 minus 3 is 12, and obviously it will be 40. Then first we'll keep this value, we'll put this value like this, like we have done in the previous video. Simply click on the spaced up spatial and click OK. Then error sum of square. Okay, we have the values for error sum of square also. Then the important thing is to get the variances. Simply divide every sum of square with its respective degrees of freedom. We have mean square due to drugs or mean square due to treatment. Then we need to calculate the mean square due to error, sum of square due to error divided by its respective degrees of freedom. So we have mean square due to treatments, mean square due to error. Simply we need to get the F variance ratio test. This is the ratio of both these two variances, mean square due to treatment or mean square due to drugs or mean square due to error. Now what we have to do, we have to get the tabulated value. For that we will use the function FINV. Then we will use the default 0.05. Then the degrees of freedom for the numerator term. Then the degrees of freedom for the denominator, sorry. Then we'll click on enter. So we have a tabulated value or a critical value which is less than the calculated value. So the first step is clear that all these three different treatments, they are different from each other, they're significantly different from each other. So in order to proceed, what we will do, we will calculate the critical difference, or for that we need to first calculate the standard error of difference of mean. That is simply square root of, usually when we have equal number of replication we used to calculate it by the under root of twice mean square divided by error, but the constant value is used when we have equal number of replicates. But when we have unequal, we don't need to write it 2, we simply have to use the mean square due to error, then multiply by, since the first treatment was replicated 6 times plus the second treatment was replicated 4 times, and divide by 4, and the third treatment was replicated 5 times. Okay, double bracket, enter. So we have standard error of difference of mean. Since we already know that all three treatments are significantly different from each other, just need to put a sign here whether they are significant or not. Then we'll simply use the function TINV, which we have done in the last video. Then the probability value is 0.05. Then the error degrees of freedom is 12 in this case. We'll click on this, press enter. So we have the critical difference value, but for that we have to multiply it with the standard error of difference of mean. Then the same thing that we have used in the previous video. If the calculated value is greater than this tabulated value, then we will put it as S. It will pop up like S. If again the calculated value is less than this tabulated value, then we will keep it like this. Simply we'll label it like NS, then these double brackets. So here it is S, that means it's significant. So here we have an evidence that all these three treatments are significantly different from each other. That means the difference among these three treatments is real, it is not by chance. Since the thumb rule is the true treatments are declared significantly different at a prescribed level of significance, which is usually chosen before conducting an experiment, like 5% or 1%. 5% usually is usually used in case of agricultural sciences, and if their differences exceeds the computed CD value, that is least significant difference or the critical difference we say. So then they are considered to be significant. That means if the difference between two treatment means is larger than the calculated value of critical difference or the least significant, then they are treated to be significant. But the important thing is that we have to be cautious whether we are using a planned pair or unplanned pair experiment, because this kind of procedure is usually used when we have a planned pair experiment. That means, for example, we have a control in our experiment and we will compare rest of the treatment with that control. Then for that we need to calculate or we need to do the things like this, that we need to calculate the least significant difference like this. But if we don't have a control treatment in our a group of treatments or an experiment, for that we need to calculate the Duncan's multiple range test, which is usually done by the other softwares also, which can also be done manually, but it is a hectic schedule or a hectic procedure rather. But by this way, again I will say that why we are doing this type of analysis in the spreadsheet of Excel, where we are doing step-by-step analysis and we have to get the sum functions, we have to put other functions. Here it is usually done to make certain kind of adjustments, which I have already said in my previous video. This is a very simple and basic analysis which you can perform if you are doing an analysis in a CRD with unequal number of replications. I'm expecting that this video will do a certain kind of preliminary help for your basic analysis if you are doing a basic analysis regarding CRD with unequal number of replications. So thank you very much. If you have any comments, then please post them on the comment sections below. Thank you.